Oh, real quick, show you a shortcut here. Is this stuff on desktop? Yeah, it's on desktop, right? So you can do sudo gcc test linked list .c clinked list.c. Those are only two files?
Isn't it H1 too?
No, but those are only two C files, right?
Yeah.
All right, so you could do it all on one line like that instead of doing the object files that we did last time, and then this will create an output file called test. So then ./test will run the program. So you can compile multiple things. It still surprised me that it didn't follow the header file stuff, but there is something called a make file. That I actually was looking into maybe showing you today, but it really is overkill for just a couple of files. So typically the way a make file would work is you would say make space whatever the name of the make file is, and it would do all this compiling stuff, effectively doing kind of like what we did right here. But it's made for situations where you don't have like 2 or 3 source code files. You have like 200 or 300 source code files or something like that when you're building something very large like that, because obviously putting a whole bunch of stuff on the command line might be problematic, right? So a make file lets you conveniently build using make space, whatever the make file is. And then it also allows you, because I mean, typically when you're building something that size, you might be, doing a build on GCC, for example. You're installing the latest version of GCC, and instead of using a package manager, you're using the make file and compiling it from source. Typically, there's then a make install at the end, so you would say make install, and that would actually copy the binaries into the correct, user local bin or something like that. So it's where it would ultimately be in the operating system. That's kind of equivalent to double clicking the setup on Windows. And typically, with any make file, the go-to move for this is you would download a what's called a tarball. So if we just do here, let's just go to GCC. Just to kind of show you how this works. Is there a source version of this? I assume they would give us a, wait, hold on. It's not very encouraging. Either is that. All right, well, let's be good enough. So I'll go ahead and grab this GCC. So a .tar.gz is something called a tarball. It's tar is a tape archive. GZ is like a zip file. Just uses the thing called gzip. All right. I'll go ahead and just unpack it. So you could do a command line thing that does the tar whatever. I think it's like tar-xvf. Then the name of the tarball, that'll unzip it and untar it, ultimately giving you a directory like this. And then I'm going to cd into that directory here. So we have something that looks like this. And notice in here we have a makefile. Now, typically, so the way this would work, if you're, you downloaded the source code of some project on a Unix machine, the first thing you would do is a ./config. ./configure. I need to configure some options. So apparently I have to give it options for this. Okay. Well, I guess whatever. So when you do a configure, it's going to kind of set up all sorts of files in here that would need to be configured. Maybe this one doesn't actually need to be configured, but this allows you to change various options for different stuff, architecture, that kind of stuff. After you do a configure, that's just changing some configuration files. Then you would do a make. And make is running that make file, and it's going to compile a whole bunch of stuff. So it said no target specified because I didn't give it target in the configuration thing. So rather than screwing around and messing with the config, that's the cadence. You do ./configure, put in the options it requires. Then you do a make that compiles everything. Then you do a make install, and that puts the executables into the correct directories. So that's how you would compile something from source. Surprised that... let's check the install directory. Oh, apparently you have to build like a certain directory structure in order for it to do the build. But whatever, what I just told you is a pretty good high-level understanding of how you would build something from source. Okay, so I think we were on desktop. All right, and we are in our C linked list here. And you want to have our linked list keep track of, you said count?
Well, I think it makes sense to just do as a struct and have that a tail too.
Okay, well, why a tail?
I mean, it'll make the end.
Add end, make add end easier?
Yeah. Well, I'm just saying if we're going for a true linked list.
Well, if you're going to go that route, typically if you add a tail to a linked list, you usually make it a doubly linked list and you have previous nodes as well. Otherwise, the only real use of tail is to get to the end quickly, which is fine. I mean, that's not a problem. So I don't really want to make it a doubly linked list, but we can do that. So we are inside of C linked list here. We're going to have a struct node pointer tail. Start that off at null. Let's go ahead and modify our current add front and things like that so that tail updates along with it. So if we look at it from last time when we do add front, we create our new node, we set the stuff for our new node. We ask if head is equal to null, we make head equal the address of that new node. We would also make tail equal head. So tail and head point to the same thing in a one list. Okay. And these guys are both node pointers, so we're just copying one memory address from a variable. We don't need any stars or anything like that. In the else, we'll set n equal to n.nextNode is equal to head. But before we, if this is always adding front, before we change head, we're going to say tail is equal to head. So before anytime we add something to the front of our list, we will preserve the current value of head in tail.
That doesn't mean tail's gonna have.
No, it won't. It won't. It won't.
You don't need to do, I don't think you need to do anything to tail there.
Because tail will initially be the original head.
Right.
And then head will keep moving forward and forward and forward, but tail is still sticking at the end. Yeah. All right, so that's add front. Get front will be this. Then you're supposed to write get end. Or was it remove end? Let's write get end and then
remove end.
just to return the value at tail. So if we come out here to test this, we added some stuff. So we added a 1, then we added a 2 in front of that. We added a 3 in front of that. A 1 is at the end. So right now we're printing out. Here I'm going to do, let's say temp is equal to get end. Then we'll go ahead and print out the payload. So this should be a 1 because that's where the end of our list is then. The front is a 3, like we saw a few minutes ago. Here, I'll show you another little trick. All right, so we have a command called history that shows you all the commands you've typed in. And then I can pipe the output of that to a program called grep, which kind of does a filter. And I'm going to grep for GCC. So it'll show me my GCC things. And this is the line I want to run, right? This guy here. So I can either copy that if I want, or I can do, Unix folks would call that bang 639. All right, so run that. It's going to ask me for my password again because I left this on the desktop. Oh, first of all, I need to throw get end. Well, this guy needs to do that, and then I need to throw this in my header file. Save, saved here, saved here. This guy looks good, that guy looks good, that looks good. I think we're fine there.
You should probably change from string to struct. That'll probably take some-
Oh, why did I write string?
I have no clue.
Didn't I copy it? Oh, no, I didn't. But then I need to go over and change it in my header file since I did copy it on that side. So there's our 3. It's giving us a 0, which means that tail is not what it should be. So add front, we take in a payload, we create a new node. That should all work fine. If head currently points nowhere, we make head equal the address of this front node. And make tail point at the same place. Okay. Else, n's next node, and n is a, I'm going to look at that struct real quick. Is that in the header file? That's a node pointer. So this should be, I think that'll do it.
No, because in here is not a node pointer. The problem
Oh, I have a normal node here. So next node is equal to head. That's my new node. And then head is equal to the address of this guy. As we add, go ahead.
I was running into issues with this in my code, and it was giving me segmentation faults and stuff because I wasn't allocating any memory to int. And so once I allocated some actual memory to the struct,
Otherwise,
would-
I gotcha. So you're doing a malloc
yeah,
size of, is it struct node? To get real memory.
right.
Otherwise, the thing is getting, it's a local variable here. Well, then why was the add fronts working?
I'm not sure. I think it was sort of working, but it wasn't like linking correctly. So it was like.
Oh,
updating
so
the head,
because
but
we
it
were
wasn't-
only looking at the last guy we added,
Right.
it was good.
It was good, but anything behind that was not good.
Yeah, I get it. Size of. Oh, so then we need to make that a node pointer
Yeah.
if we're doing malloc. So this then becomes a struct node pointer, which then means we do need to do that.
Mm-hmm.
And we need to do the same thing up here.
And you don't need to pass the address anymore.
Yeah. Head's already an address. Head's already an address. Or end's already an address. We need to bring in standard lib. Can't use malloc without standard lib. There's our 3, there's our 1. So that gives you the front and gives you the tail. And we're linking correctly. Okay, so that's get in. Now we're supposed to do remove front, remove end. Is that it?
And add in.
Add
You
end.
didn't have us do get in, but
I got you. I just wrote, okay, I got you. So let's do add end first. So we'll do void add end. This guy will take an int payload. We'll say struct node pointer n is equal to malloc size of struct node to get us some memory. Then we'll say n payload is equal to payload, and n next node is equal to null. Okay, we can ask the same question as we asked down here. If head is equal to null, we actually probably could have asked that question ahead of time, and instead of doing this, just passed it on to add front. You know, so we could say something like, if head is equal to null, then just call add front, passing it payload. Else we know we at least have a 1 list. And if we at least have a 1 list, we'll go ahead and create our initial struct. Because we're adding this to the end, we want tail to ultimately point at this guy. So we're going to say tail, which is a node, right? It's an address of a node. So tail, we want his next node to be equal to n. We don't need to say the address of n because n already holds an address. And then we'll say, so tail currently points to the current last guy in the list. Now we'll say that last guy in the list, next node is going to point to our new last guy. And then we'll say tail is equal to n, which will make that point at the last guy now, after we've updated the last guy to point at this new last guy. Okay, and you said you wanted to keep track of a count too, correct?
Well, I think it makes the other ones easier. You can
Okay.
parse it either way.
So you want to have an int count, and anytime we add something, so add end, this is a situation where count should have gone up. Add front, count goes up regardless, right? So now we'll keep track of count. If we want to have access to that, we would need to, well, unless we put it in the header file, we'll just give ourselves a get count. This guy will return count. Make sure we prototype this in our header file. All right, so we'll add a couple of things here. We'll add end, I don't know, 5, add end again, 7. We'll go ahead and do a print f, number of elements in the list, %d \n, and this will be get count. So that should return 5 there. And then this will get us the front, and this will get us the end, showing us those two values. And front. I was programming in Python for a while earlier, so I'm not in the semicolon mood apparently. Where's this guy? So was it? Didn't I declare add end? Or did I redeclare add front? Oh, I did get end, not add end. So number of elements in the list is 5. Here's the first element. Here's the last element, which is our 7. Okay. So now we're supposed to do remove front, remove end. Okay. So remove front, we want it to actually return the struct that we're removing, or do you want to just return the payload?
Well, I would think if you're actually using it, you would just care about the payload.
Okay, so return the payload, we'll extract it, so this guy will return an int. So int remove front. I guess we can just assume that this guy, I guess technically in C, we don't have to return a value if we don't want to. But in a situation where we're trying to remove front from the empty list, there is no front. There's no payload to extract. So we're only going to do something if head is not equal to null. That is, we have a front of our list. Okay, so if we have a front of our list, we're ultimately going to return a payload. So we're going to go ahead and say int payload to return is equal to, and this is going to be head payload. That's the integer associated with the payload, associated with the node that's at the front of the list. Then we need to say let's go ahead and disconnect it. So I'm going to say struct node pointer temp is equal to head. Then we'll say head is equal to temp next node, because that's going to be the new head. And then we'll say temp next node is equal to null. That'll actually disconnect it. That way we don't have any weird pointer count type stuff. Now, technically, we should also deallocate that memory. So it's what dealloc in this language. So we would dealloc temp. And let me make sure that compiles first, and I'll talk about that. In C++, it's delete. I believe in C, it's dealloc. All right, so remove front, assuming there's something in our list, we'll go ahead and grab the integer that lives at the head's payload. Then we'll give ourselves a struct node pointer, set head equal to that to preserve that. Update head to point to the next guy in the list, which could be null in the event of a one list. And then set temp equal, or set temp's next node equal to null to disconnect it. Now, for completeness, we maybe should say if head is equal to null now, then set temp equal to null. Because at that point, head and temp both, I'm sorry, not temp, tail. Because in a one list, head and tail point to the exact same node. So if I just remove the one element from the list, making head become null because temp's next node was null, I need to go ahead and reset tail as well then. So now we're back to our baseline empty list. Okay, but that's only if head's currently equal to null. If head still points to something real, that means tail's where it should be. All right, so temp's next node is null. That disconnects it. Then we'll go ahead and deallocate temp. So let me put this in our header. Doesn't like dealloc.
I think free.
Oh, is it free? Free and delete or C++ things?
Well,
It might work.
free is what I found.
See. I mean, you might be right. I thought it was malloc and dealloc because in C++ you use new and stand corrected. So free like that. And that's just a warning. So technically we don't have to return something. We can presume we're only ever going to call this function if there's no payload. I suppose I'm also never actually returning my payload here. Return payload to return. And I don't think it'll let me return a null value for an int in C. So if I'm still kicking down here, that means I didn't have anything to return. So I'll just return a -1 for right now. And what should we're not actually testing anything real right now. It compiles. So now let's go and in our test, let's go ahead and do a remove front. And we'll say int val is equal to that, remove front. We'll just hijack this printf to also print out our val. So val will be the payload that results in calling remove front, which should be our 1. All right, so this will print out number of elements is 5. Val is that. We're also not decrementing count in remove front right now. Let's go do that. We can just do it up top, since if we're inside this if statement, we're removing something. Okay, so out here, we'll load up the list, we'll remove front, we should get a 1 inside of val, we'll print that out here, then we'll get front here, which should give us our 2, the new front, and then the end should still be the 7. Again, not in the semicolon kind of mood. So there's our old front. That's not right.
It should be right here. 'Cause you're adding.
Oh, add 3. Yeah. 1 was the first thing I added. I added a 1, then I added a 2 in front of that, then I added a 3 in front of that. So that's my front of my list is 3. The next element is the 2, and it would have been 2. It was 2 for the wrong reason when I said it was 2. And then 7's the last guy. So that's remove front. And then, lastly, remove end. Okay, we can say if head is equal to, if head is not equal to null, that means we have at least a 1 list. Then we can say if head is equivalent to tail, then we can go ahead and return remove front. Now, in our remove front, are we updating tail? Yeah, we are. All right, so if head and tail are the same, that means we're looking at a 1 list. Might as well just go ahead and use remove front to handle that. That way we don't have to worry about updating tail. We don't have to worry about updating tail in the event that we just emptied the list here. Still have to update tail because we have a new end for remove end. All right, so if we're still kicking here, then that means, and if you prefer an else, that's fine. We would never be here if we hit this return, so we're not even alive, so we don't need an else. All right, so if we're still here, that means we have at least a 2 list, and we want to remove end. We know the guy we want to remove. That's going to be the payload to return is going to be equal to tail payload. So that's definitely the guy we're going to return, but now we have the issue of having our no way of getting to the guy right before tail. We have to traverse our list up to that point, which is why you like to count. Okay, because now we can run up to count -1 and then update stuff from there. All right, so kind of the coward's approach. But
It's not the way I do it. It's the right way.
no, I think it's certainly reasonable. All right, so we'll go ahead and we want to position ourselves to point at the node that's right before tail. All right, now if we had done this as a doubly linked list, well, we could have just said tail dot get prev node, and we're there, but we didn't, so we've got to run up to it. So we're going to start a node pointer, struct node pointer. We'll call this I don't know, cur node, something like that. We'll start this guy off at head. Have a little for loop. Oh, we got to do the int I here for I is equal to 0. I is less than count -1. I plus plus. And then we're going to go ahead and say cur node is equal to cur node next node. So that should zip it down the list until we're at the node right before tail. So that guy's going to become the new tail. So then we're going to, we don't need to disconnect that guy, but we do want to recover the memory. So let's go ahead and say struct node pointer temp is equal to the current value of tail. Then we'll go ahead and say tail is equal to cur node. That's going to be our new tail. we'll say tail next node is equal to null. That'll disconnect it from that next guy. Then we'll do a free on temp. Then we'll return payload to return. Okay. I stopped paying attention halfway through, but it feels okay.
We need to decrement comp still.
Yeah, we're not removing any. So if we're here, this guy will handle the decrement. Otherwise, if we're here, we're definitely removing something, right? So count minus minus here. Now it's decremented. I need to prototype this guy, right? Or did I already do that? I probably need to go ahead and test it in here too. Where's my test? So we'll remove front. Int val2 is equal to remove end. Yeah, we'll just put another %e there and do val2. Get lazier and lazier down there. So the first guy at the end will be the guy we removed from the front. The second guy should be the guy removed from the end, which should be a 7 in this case, right? So now our new end should be a 5. Our new front should be a 2. And our count is the same as it was before. Oh, same problem as the other one with the I'm not returning something always in remove end. So we'll just do the same thing. Don't need an else anyways, which makes it even worse. So there's the 3 removed from the front, there's the 7 removed from the end, there's the new front, which is a 2, there's the new end, which is a 5. So does that solve all the things? All right, so now tell me, because I presume most of you did not use free in your code, correct? All right, so if you used free, you're not allowed to answer this question. Why do we need to free the memory? Or why should we free the memory? And why aren't we used to freeing memory?
Well, when we're not used to.
Now, let's let him take a stab. Go ahead.
We should free the memory because it's holding an address space that we could use further down the line.
Okay, and why do we've never done this before, have we?
No.
So why do we have to do it now? Have we just decided we're smarter now, so we're good Samaritans?
Because we've never really dealt with memory addresses before in early process.
What do you think?
Because we never really had to working with Java because they have automatic garbage collector which goes around and picks up the memory that's no longer being used.
Yeah, so this comes back to having these nice convenience tools around us where Java always cleaned up our messes. So in Java, when you think back to the very first class, we kind of talk about Java. One of the reasons I don't use a textbook for Java classes is because many of the textbooks will indicate that pointers don't exist in Java, when the reality is that we don't have a specific syntax for pointers. Now we're getting used to using this ampersand and this star syntax for working with pointers. The reality is in Java, they're just making those decisions for us. In fact, we've been using we use pointers all over the place in Java. We could print out objects and get crazy looking Java-esque memory addresses left and right. Okay, those are pointers, right? They hold memory addresses. So we've never had to worry about it before because Java cleans up our mess. So just like there's no syntax for pointers, Java also doesn't have a syntax. In fact, I'm not even 100% sure they don't. Java might have a syntax where you can take it upon yourself to clean up memory. But does it? What's the name of the function? Is it delete?
Might be. I don't remember what the name of the function is. I know there is a way though that you can tell it to clean up stuff up.
Oh, yes.
I haven't done it much.
Okay, so let's take it a next step. I'm 100% right, sure that it does. Do you know why it has that?
I don't remember off the top of my head.
Okay. So on the surface, we might say that, oh, maybe we're just feeling, generous, right? We're good Samaritans. We're going to clean up our own mess. That's what we were always taught. Whatever. Now we're lazy. If we don't have to clean it up, we're not going to clean it up. You can actually, because if you're going to use, and we've already talked in the past about Java being low performance, right? Or lower performance than C or C++, because you're running it through a virtual machine. There is a JVM, Java Virtual Machine directive, when you actually run the code, where you can say to disable automatic garbage collection for performance. Because that automatic garbage collection, you got this little dump truck running through memory there, checking what you left behind, picking it up. That's overhead. That takes time, right? You can disable that on the, here, let's, Java, so just dash, well, it's definitely not dash J. Let's do this grep garbage. Now the option's not jumping out at me, but there is an option in here where you can disable garbage collection. You can also change, how you get, with infinite recursion, you'll get a Stack Overflow exception. Well, under what other circumstance might you get a Stack Overflow exception? As long as we're talking about weird stuff. Is a Stack Overflow exception, when dealing with recursion, always due to infinite recursion? What else could it be from?
Not out of memory.
Yeah, just a lot of recursion. You might not have infinite recursion. You just might have something that goes very deep into recursion, and before it hits its stop point and unravels, you've run out of stack space. So you can actually, with the virtual machine, you can direct it to have more stack space. That kind of stuff. Okay, so what we were doing here is we made a mess, so we cleaned up that mess with the free. If we didn't do that, is it the end of the world?
For a little application, probably not. In a big one, possible.
Yeah, because these would be effectively memory leaks, right? Yeah, so when you hear the word memory leak, it's this type of thing. Now, we got a lot of memory in our computer, and if we didn't free it, operating system still thinks it's not available. So it's not going to hand it to somebody else, because you mentioned that it's already locked down. And when we free it, we're telling the operating system he can now hand this to other folks. But if we don't free it, then we got 16 gigs of RAM. That's fine. Okay, but I think what she said is correct. You should always free memory as a C or C++ programmer, because it's the right thing to do. That's making sure you clean up your own messes. But it probably wouldn't be noticed in a small program, but if you're creating thousands and thousands and thousands of pointers, you might be creating kind of a path of destruction in RAM. All right, questions, comments, concerns, bribes. All right, risk of a quiz on Monday. No homework over the weekend. I don't know. Something we've talked about recently. Could be the free stuff. It could be something with linked lists or node pointers. Might be no quiz at all.
Can it be the free stuff?
Could it be a who?
The free stuff?
Well, it might be. I might even forget I offered to give a quiz. Because I'm not giving you homework over the weekend, I'm giving you the risk of the quiz.